Okay, welcome to the exam review. We're going to leave this completely up to you guys. It's question-based exam review, so ask away.
So the first lecture, he went over like a bunch of ways to estimate runtime that like culminated in him explaining Big O again. Like, do we need to know every step that he took to get to Big O, or should we just know Big O and that's how we do runtime scores?
I would just know Big O. You're going to want to know, so, okay, runtime. Yeah, the things to know for runtime, for sure, are Big O, Big Omega, Big Theta, and then the formal definitions of all of those things. And the little ones too.
Dr. Graham, so will give you on the exam. He's been very kind, in my opinion, and written out master method, what master method cases are.
Oh yeah.
So he has, yeah.
Okay.
Because I mean, they'll build the cheat sheet anyway. So yeah. So make sure you're able to. So he'll give you the master method for the 3 cases, but you'll still need to know what these mean.
So, for example, you should know that if we have some function f of n that's considered big O of some other function g of n, you should know that that's equivalent to saying that for all, or sorry, let's see, there exists an n naught and a c such that for all n greater than n naught, f of n is less than or equal to c times g of n. So that's just a good fact to know. You should be able to go from the big capital letters to this formal definition and back and forth. And that'll help with various proofs, etc.
There's a cheat sheet on Dr. Graham's website that has like a bunch of, I think it has the Big O stuff, but it has a bunch of other like relevant formulas that you can use, like the limit definition of little o, which would have helped you on the homework.
Yeah.
So check that out for a cheat sheet.
Yeah. Building recurrence trees and relations.
Like going code to
Code to tree. Yeah, I guess we can.
So building recurrences. I don't know, what's a good example? Heap sort?
Sure. Yeah, let's do
Heap sort? Okay, we'll use heap sort as an example. Let's say we wanted to write down a recurrence for heap sort. Okay? Wait, heap sort isn't
Actually,
recursive.
Yeah, let's do binary search.
Binary, yeah, that's a good one. Binary search. It has to. So the first requirement for a true recurrence is that you have to have an algorithm that's recursive. Otherwise, you just have a function of runtime. But it's not a recurrence unless the function recurs in its own definition. So, yeah, this is only really applicable to recursive functions. So that's why heap sort isn't really applicable. We could build recurrences for the operations of heaps, like insert, delete, that kind of thing. But heap sort itself is not recursive, it's iterative, so it doesn't make sense to write a recurrence for that. But binary search does. And the general pseudocode for binary search, because the question was going from code to recurrence, so the code looks something like this. You compare the middle element with the thing that you're looking for, the target. And then if less, of course this is pseudocode. If less, then recurse, or I guess search on 0 to the middle element. Otherwise, search on the middle element to the end. Now, this isn't the exact algorithm. Obviously, you have to actually check to see if you found the thing. So there would actually be another else if here. First we'd probably check if the middle element was the target. But the general idea stays. This is basically binary search. So here we've got some code. So if we wanted to write a recurrence for this, all we have to do is express the runtime that we see here. So we'll call this runtime t, and it's a function of the size of the thing that we took in, n. And now all we have to do is write the other side of the equation. And to do that, we just go through the code and add up the operations. So here we've got a comparison. That's constant time, 1. We've got some more if statements, some else statements, all of that stuff, that branching, that's all constant time. So we can maybe put another one here. Basically, you get the idea. There's some constant out here. Some constant time stuff. And then we call these functions either way. Either way, we call a search. And what's the runtime of search? Well, so we know it's log of n because this is binary search. But let's say we actually didn't know what algorithm this was. You were just seeing the pseudocode for the first time. What's the runtime of search from 0 to the middle? T of n. T of n over 2, yeah. Right? So building the recurrence, you almost want to try to not think about the runtime. Because if you start trying to figure out the runtime of search, well, that's a later step. First, you just have to write the recurrence. And to do the recurrence, you just identify the recursion and you write it down. So here, and if no matter which one of these if-else statements we're in, we're going to recurse exactly one time. So we have 1 times t of n over 2. N over 2 because we've divided the length of the array by 2. So that's how you would go from code to recurrence.
You want the tree method though?
Tree method?
He said it was true.
I don't know how you would build a tree out of it.
I don't know if one of you guys
So Max got us to this recurrence. Now we're going to discuss, given the recurrence, building a tree from the recurrence. And building a tree is one way to visualize the runtime of a given recurrence. So what we do is we say we start out with n. N's our first highest level. Then we drop down to n over 2. And that's this recursion right here. So our initial problem is of size n, and we recurse on one subproblem of size n over 2. If this 1 right here were actually a 2, then we would have 2 subproblems of size n over 2. However, because we're dealing with binary search, we don't need to consider that case.
Yeah, because we only recurse one time ever, this tree is going to end up looking really boring. It's going to be more of a linked list than a tree.
Yeah. And so we keep getting smaller and smaller, so n over 4. And we go all the way down until we reach our base case. And for search, our base case is a size of 1, which means we found that this is the spot the element would be in if it were to be anywhere. And so that's our base case. So our base case is size 1. And now we have to consider, so now we know the number, so now we know these are like roughly the levels that we need to consider in binary search. So the question becomes, okay, we know we have these levels. Now we need to determine the amount of work at each level in binary search. So if you go back to our code, how much work is being done at each level of binary search? We call this compare every single time. And so how much work does this compare do? Yeah. Yeah, exactly. It's constant, it's C. Because we're just seeing if middle is less than or equal to target. And if middle is less than target, we search in the first branch. And if middle is greater than target, we search in the second branch. So that's very good. So we're doing constant work per level. So we'll just do times C. Now, this is different than if we think about merge sort. Where in merge sort, we're doing more than constant work per level. So just keep that in mind. Okay, so we know that we have times C at every level. And so to figure out the runtime of a recurrence based on a tree, we have to do work per level times level. And that'll give us a total amount of work. So, as we saw earlier, work per level is C times the number of levels. Well, the number of levels is equal to how many times we can divide n by 2 until we reach 1. So, n divided by 2 a certain number of times will give us a total amount of work. And that's equivalent to log base 2 of n. Okay, and so as we saw earlier, C times log base 2 of n is just log base 2 of n for big O purposes. And oftentimes, you'll see people in math and algorithms omit this base when they do a logarithm. And that's because for logarithms, it's trivial to convert between bases. So we're not super worried about what base you use. But if you want to be, it's right there at the top. But if you want to be more rigorous, log base 2 of n would be the runtime. All right, so we just went from some pseudocode to a recurrence to a runtime using the trig method. Any questions on that?
Why are you multiplying by 6?
I was just about to say I wouldn't think of this as multiplying because
Yeah, sorry.
it's
Not multiplying, my bad.
it's more of a correspondence.
Yes.
What we're saying is for the n level we do C work. For the n over 2 level we do C work. So I would do something more like, you know, a colon or something.
Yeah, sorry, that's my fault. Good catch.
It's just an assignment. We're saying for the n level C work. And then we're adding up all of these C's. And then to add up these C's, we have to count how many of them are there. Well, that's equal to the number of times we have to divide by 2 for us to get to 1. So, I don't know. We could probably derive that, but I don't know.
Well, just n over 2 to the I equals
Yeah,
1.
n times 1/2 to the x equals 1. We're trying to get to 1. We start with n. How many times do we have to divide by 2? So this is 1 over 2
I was just adding these two.
x equals 1 over 2, which is, 2 to the x equals n. Oh, yeah. And log both sides. Log base 2 of 2 to the x is just x. So we have this n. So what we're saying here is that the number of times that we had to divide was equal to log base 2 of n. So that's how many c's we have. We have log base 2 of n c's. And c is just a constant number, so this runtime would be big O, big theta actually, of log of n.
To clarify, what you're actually doing is like adding up the runtimes at each level, right? So if like the work wasn't constant,
Yes.
it's on the product.
Yeah, so this becomes a lot harder to do if, say, this amount of work was actually a function. Like, let's say we have a really weird function, and this is actually log of n work every time. Like, maybe this is a binary search of binary searches or something. I don't know. So this would be n over 2, n over 4, log of 1. Now we'd have to add up all of those logs. And to do that, we couldn't really just intuit it. We'd probably have to do some sort of summation of log of n over 2 to the I for I, and it'd be tricky. 2, I'm not sure exactly how you would go about proving that with the tree method there, because this amount of work is not constant, and you'd have to prove something about its sum. So there are better ways to prove that runtime.
Any other questions?
You do like a quick overview of the exam itself, like which topics are probably more important to study, and which ones are less important, and like a format of it.
So yeah, so we can go through that. So the exam format, got it right here. We have, how many questions do we have? 7 questions. They're all short answer. And they're based on the topics of each lecture. So if you'll notice, we have it's up to lecture 8. So if you look at Dr. Graham's website, there's he numbers on the lectures. So every topic up until lecture 8 is going to be asked on the exam. The questions we'll ask about that'd be a big topic. So understand recurrences and how to do big O work. Understanding how to do I think there's a few lectures on sorting, divide and conquer in general. So understanding how all the sorts we've covered have worked, understanding how divide and conquer in general works is important. Understanding some of the other topics we've been covering, like the master method and the master theorem, and how to apply that to solve a recurrence is an important skill to have. The homeworks have been testing your ability to, given a new algorithm, or given a new problem you've not seen before, can you apply an algorithm to solve that problem? That's what the homeworks have been testing you on, and building that skill for you guys. So on the exam, we may ask you to, given a new problem, apply an algorithm to it. So I would just review the slides in your lecture notes to make sure with that material, you're comfortable with every component of it, and then review your homework questions, both the programming and the non-programming homework questions, to make sure you feel comfortable solving those problems. And if you have questions on any of the homeworks, written or programming, you can ask them now. We'll go over how we would think about how we approach solving them ourselves. So yeah, does that answer your question?
Just one quick follow up to that. So would we possibly doing coding at all, or is it more just
no coding? We won't ask you to actually write code. We may ask you to pseudocode to solve a problem, but we're not gonna grade you on oh, he forgot a pointer, or oh yeah, we're just gonna see did you write an algorithm that kind of makes sense that would solve this problem.
Yeah, there's no coding, but you will have to write an algorithm.
It's a lot more similar to the write-ups per se.
Yeah, honestly, the Batman problem maybe, because that's a problem where you have to write an algorithm. So
It won't be as difficult.
yeah, that's a hard, but yeah.
That's difficult. So yeah, just a more casual. So for example, scroll up to what you did for the binary search. So what Max wrote for binary search is kind of some kind of pseudocode that might be maybe a little more. That's probably a little bit more than this. But this is the kind of a round one to think about when you're writing code for exam.
Yeah, don't leave ambiguity, because then we don't know what the runtime of what you're trying to say is. If you say divide the array, say whether you mean copy it and divide it, or just move some pointers, because copying the array is linear, moving the pointers is constant. So you want to be clear so that we know what runtime you're talking about, but you don't have to actually code it in Java.
A good litmus test is that it should be trivial to go from your answer to writing a program in Java. That's a good litmus test for understanding if you've been verbose enough in your description. Yeah.
What about formal proof 3, beyond just doing recurrences, the big O, and using that notation? Are we expect to do more formal proofs, similar to 2102?
They won't be any information theoretic proofs or anything like that. But being able to prove the runtime of an algorithm is an important skill that you've been taught and you've done on the homework. So, given an algorithm, being able to prove its runtime might be something that you should be able to do. And that, using the master method is a formal proof, because some very smart math people came up with this plug and chug for divide and conquer algorithms. So not being able to apply the master method would be a formal proof.
So if you're saying like for a problem we're given a new algorithm, like a new problem with a defined algorithm, would it be similar to like how the number one problem is like sort k like this?
I don't want to. Like
that level of
it,
difficulty?
like it'll be. It's not going to be impossible, and it's going to be like a reasonably difficult. If we do ask that, then we might. It's not going to be impossible. We'll make sure it's reasonably. I've sat down and written out this exam, and taken it. And I finished it in about 45 minutes, but I've also been doing this a lot. So you'll be able to solve it within the allotted hour 15. It's not. We're not trying to like prove NP equals NP on the exam. NP equals P. Like we're just trying to like make sure you can solve an algorithm you haven't seen before. A good practice for that is to look like leak code is a great resource on like the medium leak code problems are kind of a good temperature gauge. So if you can solve one of those, in a reasonable amount of time, it's a pretty good standard. But I wouldn't sweat about it too much. You guys are prepping for that by doing these homeworks every week. That's why we've been giving you these homeworks.
Other questions?
Care how we solve certain problems. If you want to prove that something is like big O, you care if we use like the formal method that I have to show, or if you use like limits.
I mean, if we ask you to use a method, so if we might ask you, use the master method to prove this thing, then you should use the master method. But if we don't specify a method for solving a problem, then solve it however you want. Even if it's beyond the class. As long as we can understand it. And if we can't understand it, we'll ask you.
Example with the summation.
With the summation notation?
Yeah.
What's a good example of sums?
This is
Merge.
almost.
The tree version of merge sort might be a good one.
Yeah. Maybe the true version of merge sort. We go through. Yeah.
Okay. Well, let's just go straight to the recurrence.
Yeah. All right. So yeah, we'll do that. We'll do this from merge sort.
I'll see if I can pull up Bill's version of it if we need it.
Okay, so we're going to use as an example merge sort. And can anybody give me the recurrence for merge sort?
What's the divide step cost? How much work is the divide step in merge sort? I don't for divide.
Well, just the divide step. How long does it take to divide a merge sort problem?
So this divide, conquer, combine. Yeah, constant time.
Time.
Yep.
Okay, and then how many recurrences do we do? How many of them? 2? And what are the size of those recurrences? N over 2. And then the combine step, how long does it take to combine those subproblems? N. Yep, because the merge step has to go through every element. So this is equal to 2t of n over 2 plus n. So it's really easy to prove this with the master method, but the question was about the tree method, so I'll let somebody who's better at the tree method do that.
Okay, I'll do it. All right. So with this problem, we're first going to draw out our big problem, which is n, and we're now going to recurse. Okay, thanks. Onto 2 smaller subproblems, both of size n over 2. And to recap, there's 2 problems this time because our constant was 2. If the constant was 3, we'd have 3 subproblems, like a 3-branch tree. So we'll keep going down. Now, some observations to make. If you add up the amount of subproblems on each level, there's n problems on each sublevel. And just like the past problem, we're going to divide all the way down until we hit our base case of 1. And this is going to be a total number of levels log base 2 of n levels. So when we're trying to understand, so any questions on the way I drew this tree and how I arrived at this tree? Okay, so that's our tree, and now we're trying to figure out how much work is being done at each level. And what it looks like is we have n work being done per level, and we have log base 2 of n levels. So if we wrote that as a sum, that's the sum from I equals 0 to log base 2 of n. And we're doing that on n. And so that results in n log base 2 of n times I.
Any questions on how we got n work at each level? No? Okay.
Yeah.
When writing this out on an exam, are we expected to like do the full, like say step by step as far as show like the summation symbol and all that, or can we just kind of draw the tree, obviously like as in, like the notes have like problem size, like far left column, like in over two, like you have drawn the left, and then like have a tree kind of in out, and then like have a corresponding level like in over two plus over two plus n, and then just the end is sort of like I guess show like write like the summation.
I mean, so this summation solution, we're not requiring that you write it this way. Like, you don't have to do it. We just did the sum because the question was about what a sum might look like. But as long as it's like a logically tight demonstration of the runtime of that algorithm. So as long as there's no like logical leaps that you're making saying, oh, then it must be like if you go from like if you just draw this tree and say log 2 of n levels and say, oh, runtime's n log n. Like we're not gonna be able to understand, we're not gonna be able to piece together how you arrived there.
So
But
if you like have like the tree and you have like put like right next to that every corresponding level like the word like
done per level.
n plus n over two plus n over two equals n and like so on through to the levels and then at the end you do like say like n over like log base 2 of n levels times n work on each level equals like n log 2.
Yeah.
Is that enough?
Yeah, that would be good because then you're demonstrating. Then you've proven to me how many levels there are, and you've proven to me the work done per level.
Okay.
So then you've demonstrated to me. Yeah.
So is it big data in that log n?
I mean, yeah, merge sorts, big data, and that like.
So every time you use a tree, you have it like that, it's just big data.
I think so. It just depends on the tree itself, because it's possible you have shrinking work per level. And if you don't capture that appropriately, then you might need to do a big O bound. That's a very problem.
Yeah, I would try to avoid the tree method honestly because it can be very misleading sometimes.
Any scenario where you have the tree method, you can apply the master method.
Yeah.
And
So yeah, so like the misleading example here is let's take quick select. Quick select was t of n equals t of n over 2 plus n. Okay, that was quick select. And the tree would look something like this. n over 2, n over 4, 1. So it's the same tree as for binary search, but now the amount of work we're doing at each level is n. But it's the n of the node we're on. So this is n over 2, n over 4, 1. So you'd have to add that up. And this would be I equals 0, log base 2 of n, over 2 to the I. Right?
Wow.
that would be good.
Plus n.
So here, does anybody know what that sums to? I don't. So that's why I wouldn't use the tree method for this. If you just look at this and say, oh, it's on the order of n work for log n levels, oh, it must be n log n, you'd be wrong. It's n. So that's why I avoid the tree method. It can be very misleading. If you want to use the tree method on this problem, you'd actually have to solve this summation. And I personally, I mean, maybe it's like,
We just pull the end
it's
out.
geometric, I think.
Yeah, it's too much.
So it'd be like a over 1 minus r, something like that. But it's a function, so I don't know what would happen. Basically, I avoid it. Because you would get the wrong answer by just assuming, oh, it's on the order of n work log n times.
To the n over 2 to the I.
Yeah, but I starts at 0.
So the 0th level.
When I is 0, 2 to the 0 is 1. So we'd be doing n work, which corresponds to that level right there.
So why would the summation be
2
2?
to the n?
No, 2 and then 2 times n.
Because the amount of work per level is 1/2.
I think it would be 2n.
Yeah, it would be 2.
Oh,
But you'd have to,
sum
that's
equals.
the
Oh,
answer to
sorry,
the
I
summation.
misunderstood
Yeah,
you.
yeah.
That's,
So
that,
if you can solve the summation, then you're good. But it's just a lot of people skip the summation and they just look at the tree and they're like, oh, it's obviously n log n. So that's why I'm saying the tree can be misleading. If you're rigorous with the summation and you make only valid steps, then you'll only get valid results. But it's just sometimes hard to get there. So you're right. Yeah, this would sum to 2n, and that would give you the correct result. The answer is theta of n.
So do we have to know the tree method? That's what trees look for in other words, know how to do master method.
That's the thing. Yeah, we're giving you the master method apparently. So
Yeah.
Wait, we don't write down.
yeah, it's given on the exam.
yeah, I thought this, but he decided Dr. Graham is very nice to you guys.
Now I don't know which version he's giving you.
Give him both versions.
Both versions? You're getting both versions apparently. So
Just the equation or the full text?
probably just the theorem itself. The theorem itself says like, you know, big O at let's see, f of n, big O of n to the log base b of a minus epsilon implies t of n element of big theta of I forget something, but it would. This is probably the format it would be given. Just raw
Like,
implies, you know, no explanation. So you should still know how to use it. Be familiar with it, but we'll give you the
usually the 3 cases.
cases.
Select, can we assume it will be n over 2 for the reduction
Can you assume?
when analyzing select?
Um,
You guys have that over 2 here, but
can you explain that? So, what part are you saying?
T n over 2.
Yeah,
Is that a reduction?
is this a reduction
Or like,
or recurrence really?
That is the recurrence for quick select.
Yeah, that's
So-
the recurrence.
Unless you do like a fancy version. No, it's always that. At least the versions that we showed.
I mean, you can assume that this boils down to 2n. You can't make that assumption. But that is the. Sorry, I'm not sure I understood the question.
does the quick select have like a worst case of master? Actually, right now, that's never mind.
All right, you feeling good?
Yeah.
Okay. Yeah.
So you showed how like it'd be hard to do that with the tree diagram method. Can you go and like basically do it with the master method? To illustrate how you do it?
Sure. So, I see your pen, Max.
Mhm.
So the master method, just to remind everybody, basically says, given some recurrence t of n in the form of A T
I got it straight.
n over b plus f of n. So the match method requires the recurrence be in this form. Now, just to rewrite the recurrence, we have t of n equals plus n. So a equals 1, b equals 2, and f of n equals n. Okay. Everyone comfortable with what this general form means? And this is the quick select equation. And this is just it broken down where I outline what A, B, and f of n are. Everyone good with that? Okay. So basically I look at my cases. So case 1 says if f of n is in the member of big O of n to the log base b of a minus epsilon for some epsilon greater than 0. That implies t of n is a member of theta. I don't know all of it out, but it implies that it's a member of a set of n log. So let's see if we're in this case. So n to the log base b, where b is 2, of 1 minus a sigma.
Epsilon.
Minus an epsilon, sorry. And f of n is n. So, can we select an epsilon for which that is true? Where epsilon is greater than 0?
Simplify log base 2 of 1.
No, so we can't. So log base 2 of 1 is 0, and log base 2 of 1 minus anything, any positive integer, is going to give you some answer that's not 0. So it would be too small, it'd be a fraction. And so we can't apply this case. So now we examine case 2. Case 2 asks, is n the member of some big theta such that n log base b, in this case b is 2, of 1 times the natural log of n raised to some k. So are we in this case where n is big theta of n log n? No, we're not in that case. So then we go to case 3. And we say, is n, or is f of n, big omega of n to the log base 2 of 1 plus some epsilon such that epsilon is greater than 0. So, is this true? Yeah, well just give me some epsilon for which that is true. What was that? 1. Okay. So an epsilon is 1, log base 2 of 2. That checks out. So we know it's true for some epsilon. So that tells us so you can't stop there with case 3. Because with case 3 we also have the regularity condition. And so the regularity condition says,
Not log base 2 of 2.
well, that he chose epsilon of 1.
No, but you add the epsilon to the
Oh,
outside.
sorry. Good point. Sorry. Andrew just pointed it out to me. He just reminded me, sorry, that it's log base 2 of 1 plus epsilon. He just reminded me of that. Sorry if I confused anybody. So this, in the exponent, this is like in parentheses plus epsilon. Sorry I did not make that clear earlier. But that still holds. Log base 2 of 1 is 0, and plus 1 would give you n as big omega of n, which is true. So the regularity condition says a of f of n over b is less than or equal to c of f of n for some constant c less than 1 and a large enough n sub 0. So a in this case is 1. Yeah, a is 1 and b is 2. So a is 1, f of n over 2 has to be less than or equal to some c times f of n. Now, f of n in this case is the actual function n for some constant c less than 1. So is there any c less than 1 such that this is true? And just a reminder that in this case, f of n over 2 would just be n over 2. So we can reduce this to. So, I mean, you just choose c equals 4/5 and that's true. And so then we've demonstrated that digital occurrence t of n is a member of big theta of f of n, or in this case, n. So that's walking through an example where we examine all 3 cases of the master method and see we only make it in the last case. So was that helpful?
Yeah, definitely.
Okay.
So if you have like a bunch of like case cases, do you have to go through and show each case, or do you just go straight to the case and it's like,
That's
oh,
exactly
it's that case?
that's exactly what I was going to say. In the test, you do want to be fast, and so you actually don't have to linearly go through every case. If you have a hunch, you can go with that hunch, or you can do what I like to do, and that's just, we've got our f of n, we know f of n. F of n is n. And we know log base b of a is what?
Log base 2.
Log base 2 of 1, which is 0, which means log n to the log base b of a is 1. And in every case, we're comparing f of n to log base b of a. N to the log base b of a, sorry. So here, just by looking at this, how does n compare to 1? Is it O, theta, or omega? If we were to write n is an element of something of 1, what would that thing have to be? Omega. This would have to be omega. And so we know we're in the omega case right away. You can just compare f of n to n to the log base b of a and figure out what symbol you're at. And then you can use that to guide the case. So that's kind of like a constant time way of hashing to a case.
If by showing that the first 2 cases can't possibly be true, is that sufficient for showing them the third case?
No, there are many recurrences that don't fall into any case. So
That's a great question.
Yeah.
So even if your master method actually shows that no case is true, it might end up being that doesn't fit into the master method, and you do some kind of tree recurrence or some other method of finding the runtime.
oh, that. What is that? Wait, actually, that actually works.
Just do like
Well, okay, here, yeah, let's do like over n log n. There we go. That's like, you could prove that that's not case 1 or case 2. That does not mean it's case 3. So, yeah, you gotta show. You can go straight to the case you want, but then you do have to show that it is that case by picking an epsilon and showing the regularity condition if you have to.
You're saying it's none of the cases, we still need to go on like Permit's mother method?
Yeah.
But that doesn't apply to master theorem. How do you know?
yeah, tree method,
Yeah.
something along those lines. You can also do like a guess and check if you get really lost. You'll always eventually get there with the guess and check, but I recommend you exhaust your other options before going to the guess and check.
I don't know how to solve that, by the way. I mean, that's weird.
Yeah, I'll give you one hint on. I'll give you one hint on the test, and it's not. This is not a problem you'll be able to solve.
Yeah.
We're not going to ask you to find the runtime of that. A problem involving substitution.
How about the homework problem?
Yeah, let's go to
Let's
the
do the
homework.
homework problem. Because I don't want to do the same problem for the third time.
That's kind of boring.
Yeah.
All right,
Do we have the homework problem?
I can.
Slash the solution?
So we use an extra exam. Just finding one
Where are the
case is not
solutions?
right.
Heat
If you
mail
prove,
it
if you prove it exists in one case, then you've proven that
I don't
it
think
falls
I
in that
ever
case
saw
in the
that.
master. So yeah. I'm gonna grab up the solution. Oh wait. Dr. Graham didn't remove the requirement to do the solution.
What do you think?
For substitution, Dr. Graham removed the,
The answer key is right, it's just the wrong
oh,
problem.
this one right here.
Yes.
Is it this
Okay.
one?
So, do you guys have the actual problem?
It's problem 4. Can you pull up the actual? I'll pull it up. Sorry, we haven't done this homework in a while. Let's pull it up.
Because the actual problem, the answer is correct, but
Right.
the actual problem is incorrect. Oh god, am I going to be able to do this? Substitution is hard, so we'll see if this goes well.
There it is.
T of n, what is that?
2t square root of n
T square root of n
plus n.
plus n.
Right.
Okay. Uh-huh.
Wait, so you like the master method, right? But you think substitution is hard. So like, I feel like those are running in opposite directions.
So you
you're
use-
hoping that you don't have to do substitution.
Yeah, honestly, yeah.
Okay.
You're hoping.
You just hoping.
You need to be able to do it, but I always, every time I try to do it, I struggle through it. So,
Do you want me to do it?
yeah, you
I
gotta
can
do
do
it. I did
it.
it last time.
Yeah.
Here's the solution.
Yeah. So remember that the idea of substitution is to recognize, okay, I'm a pretty clever student. I know that this is kind of ugly. Square root of n plus n, I have 2. That looks complicated. But I can't find the recurrence.
This is
Of-
the solution for this.
I can't find the solution of some other problem. So where did I put this? Oh, there it is. So I'm just going to guess an m, some substitution value that makes this an easier problem to deal with. And if you'll remember from calculus, U substitution and UV substitution are a similar concepts. So it's drawing on the same skill of kind of being able to guess your way to it. So in this case, I'm going to guess that my m is going to equal log base 2 of n.
I don't think that's the right solution. It's the solution for the wrong problem.
That was the solution for this problem.
No, it's not.
No, he wrote that incorrectly. It's fine.
Are you sure?
I'm pretty sure.
Well, look, this T of n here is the same problem as here.
I'm pretty
The
sure.
substitution is correct, but the
This solves this problem.
It's a different problem. That has square root of n.
I don't think this is supposed to square. I think that has. I think this is supposed to be n. I think that's the error.
Oh, okay.
Yeah. Sorry. Okay. So what I would say is I'd plug in. So if this is m, then n equals log base 2 equals 2 to the m. Does that make sense? So this is just algebra to get from here to here. That's just if you raise each side to the power of 2. If you take 2 to each 2, if you put this in the exponent of each side, you're going to get this algebra right here. So that implies that. And then when I substitute, I get 2t, and then the square root of 2 to the m over 2 plus n. Well, an n in this case is just 2 to the m. So that's still pretty nasty, but luckily I'm going to define.
Yeah, question?
Why is it suited into the 2 in this group?
Oh, sorry. Okay, my bad. You're right. So this equals 2t of 2 m over 2. Sorry, good catch. So this is still ugly and a little bit hard to manage, and I want the form a of a times t of n over b plus f of n, so I can apply so I can apply the master theorem to solve the problem. So I'm a clever student, and I say, oh, well, let's find another function s of m that equals t, and this s of m can be anything. It's just s is just the convention, it's like the convention of what you typically say. And so now I substitute this in. So anywhere I see t of 2 of m, I just plug in s of m. So s of m equals 2 s m over 2 plus. Does that make sense? Does that feel good? And so from here, you can apply the master method and figure out what case you're in. In this case, I believe you're in case 3. I don't want to do that right now. So if you guys really want me to, I can do it. But I'm pretty confident you'll be in case 3 here. Because from Max's clever trick in the master method, f of n equals 2 to the m, I guess f of m in this case, and n to the log base b a gives you that. So this grows faster than that, so we're probably going to be or m. Does that make sense? Yeah.
How are you just able to change, so like, in the step right before you go to case 3, how do you, like, why is that 2s and not t?
How is this 2s? So yeah, so maybe I should make this step more transparent. So anywhere I have an equation in the form t of 2 to the m, I can substitute s in it. In this case, I had t of 2 to the m over 2. Well, 2 to the m over 2. So if I have another function, just to kind of like make this point clear, let's say I have a function g of x equals 2 to the x. And then in that case, g of x over 2 equals 2 to the x over 2, right? So does this make sense right here? Okay, so the same kind of thought process follows here, where this is like saying if I say s of m equals t to the 2 of m, then if I have s of m over 2, that's equivalent to t 2 to the m over. Sorry.
Yeah, I see.
You see what I'm saying? Yeah. Okay. Awesome. Everyone else see that? This step of how I say s of m over 2, I substitute m here for m over 2, and then I have this equivalency. So I can make this substitution from here to here. That's a good question. That's a very non-obvious step. All right. Yeah.
You can try substitutions where instead of trying to change the form of that work done, it's like outside the recurrence. Like, for example, you say like n is equal to 2 times the square root of n. And like, so basically try to transform what's in those parentheses rather than transforming what's outside.
With the where I transform like what's here.
Yeah, so I'm saying like, so could you say like m is equal to like the 2 times the square root of n, so then the recurrence would be like 2 times t of u divided by 2 plus u squared over 4, and that's already like in the master theorem. Like basically what I'm saying is like, yeah, instead of trying to transform like the n into the 2 to the m, like on the outside, can you try transforming what's in the function?
So you're saying doing something like this, m equals 2 square root of n.
Yeah.
And then that would turn the, so yeah, what that would do here is it would turn our recurrence into t of m over 2, right? Yeah?
Yeah.
And then what would that turn this into?
I'm squared over 4.
Yeah. But here's the problem, it would turn the left side into that too. And
Yeah, you're right. the math method does not apply here.
Yeah, I don't know how you would get rid of that
Well, I think you-
parameter on the left
I
side,
think you just said S of M equals that.
but then I think you would
Yeah.
undo the niceness of
Yeah,
that.
that's true. You would. Yeah, you just end up in a circular problem.
Yeah.
You're right. Yeah, I mean, if you have like a very neat example of what you can walk through, I don't have, the only on the top of my head that like comes to mind.
The reason we did that substitution is because it absorbs the square root while keeping the left side generally
Pretty.
approachable. Here, I'm not sure how you would approach that. Let's see. So we got
Oh, it's actually case 1. It's case 1 of the master theorems. If you want to just walk through that.
log base. Yeah, that's a different problem.
I mean, I can just.
Log base b of a. B is 2, a is 2, so that it is just n. 2 to the m is big omega of n, right?
Yeah.
And so, in fact, we could pick any epsilon here. Epsilon could be 1, could be 100, doesn't matter. But we're definitely in case 3. We could show the regularity condition. I won't show that. And so, yeah, the answer, we would say that S of m grows at the rate of 2 to the m, I believe, because that's f. Yeah.
Yep.
And then
Substitute everything.
we would have to substitute back. Yeah. So
Could be some long, nasty recurrence.
I never actually did that step. Oh, how do you substitute that back?
So what you say
S
is.
of m is t of
So you have to say T of
I think you just substitute that back in the original.
oh, you're right.
I think you just plug m, like it's 2 to the log base 2, which just ends up being n. I think it's just n. Yeah, pretty sure it's just n.
That's what the other technique gave. I don't know if that's a coincidence.
No, yeah, I'm pretty sure it's n. I think you actually don't. What you do here is you just say, our original m substitution was this. M is log base 2 of n. So
oh, you're right. You substitute that.
2 to the log base 2 of n is just n. So it ends up being n.
If you want more practice on that, just like I'm sure that Carnegie Mellon and MIT published their like practice substitution problems and just like walk through one next to the solution.
That kind of makes sense in this scenario. If you just look at the recurrence, this doesn't follow the master method because we have that square root. What is that square root going to do to the size of the problems relative to just dividing by something? I mean, in the master method, you divide by b. That's going to cut the problem down by some constant factor. Square rooting it is going to decrease it by even more. So here, more of our work is coming from this component than it is from this. So this overwhelms, and that's why it's n, intuitively.
So this is probably just a bad idea then. But if you're using the logic of like intuitively that it should like reduce the search space faster than divide by 2, can you just kind of say like, oh, like the square root of n is like theta n over 2, so I'm just gonna put n over 2 in there instead.
That's a bad idea.
That's a bad idea.
It's exactly what I said. It's intuitive, but it's not a proof.
Intuition's
Yeah.
A lot of things seem intuitively right, but are actually wrong.
Yeah.
Like RSA seems intuitively right.
Yeah.
Yeah, we got an exam as well. this is gonna be a what?
Or the answers to these problems gonna be posted for us.
I think they're posted.
We're not posting the solution, right?
I
Because
Because they want to reuse it.
oh, it's Professor Hott's prerogative. So the other algorithms class has this problem set as well, or a variation of this problem set. And so I'm not sure if I think we're handcuffed by Professor Hott, and whether or not he wants to release his solution.
You're welcome to book some office hours and we can go over the solution, but I'm pretty sure the solutions will not be released.
That's a good point. If they are, Dr. Graham will email you guys, and it'll be very obvious.
Other questions?
So, the material goes through the lecture feed. Like on the, the course website, see those lectures numbered. It has it says number 8 bouncer trees, 2 trees, red black trees, and blue trees. Then PDF notes for the one before that, 7, which was mass method, and Kuratsuba, that says lecture feed as a PDF. So does it include the material include bouncer trees, 2 trees, red black trees, all that?
Yeah. Yeah, that's it. Did you guys all do the homework?
Yeah, raise your hand if you've submitted an attempt for the homework.
We're just wondering.
All right,
The
all right.
last homework or
The current homework, the bird scooters homework. It's Camp Prune.
Prune.
Yeah, who was stuck on the pruning?
So Cam posted some material on
Oh,
that on Colab. So if you check Colab, Cam pushed up some notes that might help you with that. Like a detailed example of how pruning works.
But there's there's no partial credit for the 10 test case. That was literally just 10 out of 10.
Yeah, yeah. We did it that way so you feel like you have progress. I feel like it's not harsh to go from 0 to 1, like, oh, I'm done. I feel like that was too harsh. So that's why we did it that way. Was it better having seen them all separately, or do you prefer it when it's all one? Is there a preference?
I like to.
if the test cases are visible, we can usually see where we have problems.
So we like separate test cases. Yeah.
Yeah, because usually those test cases will test different things. Like I remember there was this one homework where we had 4 test cases and I passed 3 of them and I realized we got a 4th test case.
Okay.
So I think it's more useful to have separate test cases.
All right. We just
Especially when you can download the test case file automated.
Just wanted to check in on that. All right. Anything else for the test? You guys get 1-page cheat sheet in your own handwriting. Just 1 page, just front, yeah.
So for quick select, it was T of n over